So I think we are ready to start. So welcome to the afternoon session, and it's a pleasure to welcome O.Philipsen as the first speaker, talking about the QCD chiral phase transition for different numbers of quark flavors. Yeah,
thank you very much for the invitation to the beautiful place here in early spring. I want to report on some work that got published last year on a very old question, namely what is the nature of the chiral phase transition when you change the number of quark flavors that you take into account, the massless ones. And this is work done with Francesca Cuteri and Alessandro Sciarra. Okay, so the topic was more or less made prominent in a seminal work almost 40 years ago by Pisarski and Wilczek, who outlined the two scenarios that are shown here. So what you see is the so-called Columbia plot, which tells you the order of the thermal phase transition in QCD. In this case, you have 2 + 1 flavors. So the horizontal axis parameterizes the UND quark mass is taken to be degenerate from 0 to infinity. And the vertical axis parameterizes the strange quark mass. And then, you have a first order phase transition in the neighborhood of the pure gauge limit. This is well known. And of course, we're interested in the chiral transition. And Pisarski and Wilczek did a renormalization group flow study in linear sigma models augmented by a TOF term for the U1A anomaly. And they looked for fixed points, and their prediction was that the chiral transition is always first order when you have 3 or more flavors. So the 3 flavor situation would be sitting down here in the bottom left corner. And the situation for 2 flavors depends crucially on how strong the anomaly is, or whether U1 axial is restored or not. And the statement then was that if the symmetry is restored, then you have larger symmetry, which would drive the transition first order. That's the left scenario. And if it's broken, then it should be in the O4 universality class. That was later a second option was found by Belisetto and Vicardi for a somewhat larger group. And if you're in the right scenario, then you would have a change in the order of the phase transition when you go from 2 flavors to 3 flavors, okay, lower left and upper left corners. And if that happens, then you must have a tricritical strange quark mass in between that separates the two limits. And obviously, this is all interesting for phenomenology because the light quark masses in nature are very small. So the question is, are you in the neighborhood here of an O4 transition or of a Z2 transition or of a tricritical point, etc.? So there has always been strong interest. Okay. One more thing we will need later on is if you're below this tricritical strange quark mass here, the chiral limit represents first order transition, but it's in fact a first order, it's a triple line that you see here, and you can understand this if you draw the TM phase diagram as on the bottom here. Then you have at the critical temperature, you have a 3-state coexistence between chirally broken phase with either psi bar psi positive or negative. Okay, you can relate them by an axial rotation. Or in the symmetric phase, you have chiral condensate 0. So this green line here is a triple line, and the endpoint of a triple line is a tricritical point, which then matches on to a second order line. Okay, so this was the prediction, and then there's a 40-year history of works, which is too long to repeat. I have a review and a summary with, I think, hopefully halfway complete reference list. Recently, let me just summarize the findings over the years. So if you start this with unimproved lattice actions and you go to coarse lattices, what you see is the situation on the left. So you can see a first order region even up here. That took a while to make quark masses small enough, but you can explicitly see that. And then if you make the lattice spacing smaller, this boundary line, this Z2 boundary line that delimits the first order region shifts to the left towards the chiral limit. And so that's indicated here by the arrows. And then you all know the chiral limit can of course not be simulated because the fermion determinant is singular in that limit. So it's a problem. The line is running away from you, and it gets harder and harder to follow it. That's what's making this so difficult. And the question was, does anything remain in the continuum limit? If you take A to 0, do you end up on the right situation, or do you stay in the left? And another confusing thing is, and we'll hear more about that from the following speakers, is that if you take highly improved staggered actions, then essentially you don't see any of this yellow first order region at all. It seems to be pushed to excessively small quark masses. Okay, let me just illustrate this with two examples. So here is an example. We are looking at the 3-flavor boundary. So that's this point here. Okay, and you see the critical pion mass that parameterizes this location of the blue point. So the boundary where you swap from crossover to first order. And this is plotted versus 1 over n tau squared, which parameterizes lattice spacing squared. And this is work where our chairman was involved together with Philippe de Forcran. So here is the 3-flavor situation. You have n tau 4 lattices, n tau 6 lattices, and you see the first order region shrinks, right? So your first order below the line and crossover above the line. And then the violet curve here this is a 4-flavor situation, and you see the same situation. So you have clearly a first order region, but it shrinks. And then when you try to extrapolate, it's not so clear if something remains. And as I was mentioning, you don't even enter this yellow region at all if you take improved actions. The same situation you have when you look at Wilson fermions. So again, this is a 3-flavor situation, and this is 5 years worth of simulations, and this is an order A improved, non-perturbatively order A improved Wilson action 3-flavor situation. Again, you see very clearly a large first order region, but you see it shrinking. And again, the extrapolation gives you qualitatively different results depending on which polynomial you take. So the continuum limit is not clear. The smallest boundary mass here that's available is 110 MeV. That's smaller than the physical pion, of course. And another thing that is confusing, if you compare the two, you see, if you look on the left scale, compared to the previous one, the first order region for Wilson is much larger than the one for staggered. So there was a lot of confusion, and the question is, what's right? You change the action, you get drastically different results by factors, okay? We're not talking about 10, 15% effects, we're talking factors here. So this is very confusing. Okay, and then a few years ago already, Francesca and Alessandro and I started to think about this in a slightly different way, and we think we have come up with a suggested solution to the problem, which gives you a unified picture. And you want to switch viewpoint a little bit. So the strange quark mass here is the parameter in this Columbia plot that smoothly interpolates between 3 flavors down here and 2 flavors up here when you make it infinitely heavy and it decouples. But you can make this interpolation in a different way when you write down the partition function like here, and you have integrated out the fermion determinant. Then if you have degenerate quarks only, then you get a power of NF up here in your determinant. Okay, and now since we're working with staggered fermions, all the practitioners know that for the staggered fermions for a single flavor, you have to take the 4th root anyway, right? So if I take the 4th root, then I can as well take the 4.2 root or whatever. So we said, let's continue this to continuous values of NF and see what happens. And so now you have the translation here to a new kind of Columbia plot on the left-hand side, where you have mass going in this direction. And now everything is degenerate, and you have NF going in this direction, and then this picture translates on the right translates to the picture on the left. And you see now, instead of having a tricritical strange quark mass where you change from first order to second order, you have a tricritical number of flavors where you change from first order to second order. And this, now you can say, okay, that's just equivalent, but what does this buy? This buys you two things. And one is that now both scenarios that you are trying to distinguish have the same feature, namely, now you see this picture on the right doesn't have a tricritical point. But if I translate it in the other Columbia plot on the left, it now must have one. And that is the case because we know that for one flavor only, there cannot be a chiral phase transition because you cannot rotate in flavor space. So the phase transition must go away. Okay, and it can only do that because you're coming from a first order region. It can only go away. This is, by the way, now the triple line on the bottom here. It can only go away by having a tricritical point. And so now I have two situations. I have a tricritical point in any case, and the question is it between 2 and 3 or is it between 1 and 2? That's advantage number one. Advantage number two is that if I have a tricritical point, then that comes with its own set of critical exponents, which are mean field, because the upper critical dimension is 3. And that means that this second order line here, the boundary, the Z2 line that comes out of the tricritical point, enters the tricritical point with tricritical exponents. And this is what you see like here. So you have a scaling field, the mass, the quark mass is your chiral symmetry breaking field. And this Z2 boundary line is guaranteed to come into this tricritical point as a power series of AM to the 2/5. Okay, so I don't have to distinguish very nearby sets of critical exponents, O4 versus Z2. I know this has to be tricritical, and I know what my expansion scheme here is and how I can extrapolate. Okay, so this is all continuum. And now you can imagine you have a third axis lattice spacing or n tau that goes, let's say, into the or perpendicular to the plane here that we are seeing, and then this tricritical point will be a tricritical line. Okay, and now I'm guaranteed this is there. I don't need to worry anymore, is this there or not? The only question is, where is it? And this I can find by seeing if I reach the scaling regime and then extrapolating with this known form. Okay, so the way we're doing this is standard, and I'll be very brief on this. We've done this for probably a decade or so. This is statistical mechanics. You look at the order parameter, which is psi bar psi, and then you compute generalized cumulants, and they give you information about the distribution that you generate in your Monte Carlo simulation. And from this, you can extract where the transition is and also what its nature is when you do finite size scaling. It's excessively expensive. And so first you find where the phase boundary is. That you do by the skewness, so you have equal weight on the two flip-flocking phases. And then when you want to find the boundary between crossover and first order, you do this by the Binder cumulant or the kurtosis, which is shown here. So here M is varied as a parameter, okay, and on the left you're on the first order side, on the right your crossover side, and the intersection here between different volumes, that gives you the critical point, and its value is universal for 3D icing. This is 1.6. Okay, and the strategy now is we investigate staggered fermions, unimproved, and we're just looking at the bare parameter space of bare lattice parameters, which are the lattice gauge coupling, the bare mass, the number of flavors, and n tau, parameterizing the lattice spacing. So I have a 4-dimensional parameter space. Now I'm looking for the phase boundary. Then I have a 3-dimensional subspace, all of which is phase boundary. And then I'm looking, where is my boundary between first order and second order? And now I'm down to a line. Okay, so a surface, 3D, 2D, a surface. So what we're doing is we're looking by this cumulant investigation for the chiral critical surface in a 4-dimensional parameter space of staggered lattice fermions with NF flavors, and NF is tuned continuously. Okay, so here are the results, and every data point now is representing you one of these intersection points. Okay, so that takes a bunch of temperatures, a bunch of masses, a bunch of volumes, and all together what you see is about 120 million Monte Carlo trajectories in the light mass regime collected over the span of almost 6 years. And now what you see is always the same data in different representations or projected on different parameter planes. So this is essentially the lattice version of this Columbia plot, which I showed you. So mass over temperature as a function of NF. Okay, and above you're in the crossover region, and you see the first order region, and you see what I've shown you before. The first order region gets larger when you go from 2 to 3 to 4 flavors. We've seen this before. And if I wouldn't put an NF label, you couldn't distinguish which are integer or non-integer NF. So this all works nicely. And then the top curve here is n tau 4, then comes n tau 6 and n tau 8. So we have now 3 lattice spacings. Okay, and they are surprisingly linear, all these curves. And what we're interested in is, of course, the intersection here, which is the tricritical point. And this you can only see when you zoom in. This is done on the right. This was the first publication on coarse lattices. So here you see, if you take only NF2 and NF3, then of course you don't see the functional behavior, but you see if you fill in that this nicely approaches leading order scaling curve. I have rescaled my variable here. And as a very nice check, you can do the same thing, which we have done years ago already with Claudio and also Massimo, where we looked, instead of NF, we looked on the imaginary chemical potential dependence, and you see the same kind of tricritical scaling. So there is no doubt this tricritical scaling is there. And that's this point. So there is perfect match. Okay, so what this tells you is that for 2 flavors on n tau 4, this staggered theory gives you a first order chiral phase transition. Okay, but if you now go left, you take the n tau 6 curve, you see now the intercept is somewhat larger than 2, so it falls out of the first order regime. Okay, and that's the tricritical point. So you would say everything to the right is first order, and 2 flavor now has moved into the second order regime. And now we thought, okay, question answered. We have answered the 2 versus 3 flavor question. But now a new question arises when you look the n tau 8 curve. That's this one here, the yellow one, a bit hard to see. The question is, where does this intersect now? Does it keep moving to the right? And what happens to the 3 flavor situation as you make your lattice still finer? And now you can get a better idea of this by just looking at different parameter combinations. Let me skip this maybe. We can use this for the questions. So here is again rescaled quark mass. But now I'm not plotting the flavor number here, but I'm plotting n tau. Okay, and that's interesting because this takes out this almost linear behavior. And note that this is again the rescaled variable, and you see I have 3 lattice spacings, okay, 4, 6, 8 for some of the flavor numbers, not for all of them. And you see there is very little curvature in this. So we're close to scaling behavior again. And indeed the lines are an extrapolation using a next to leading order scaling ansatz. And then you would get tricritical points here. But now we're not guaranteed, if you fix NF, you're not guaranteed a tricritical point. So let's see what the alternative is. The alternative is that your curve would end up here in the origin, then there would be no tricritical point. And if you try to fit that, that would go by ordinary polynomial expansion, right? You would have a critical quark mass in the continuum, and that would get modified by order A and order A squared corrections as usual. So you would have an ordinary polynomial expansion. And if you plot AM, the continuum limit is always on the lower left corner. And what you see even here by bare eye is that these polynomials don't even go through the points, and the chi-squareds are larger than 10, or one curve goes negative. So this does not describe the data. tricritical scaling does describe the data, but then you have a tricritical point on the bottom here. And then if you have a tricritical point on the bottom here, the interpretation is clear. If you have a first order phase transition here somewhere and you make your lattice finer and finer, meaning larger in tau, continuum limit is in the left corner, eventually you run out of the first order region, and in the continuum limit, your phase transition will be second order. Everything to the left here in the chiral limit of this tricritical point is second order. And the shocking thing is that this is the case for the entire list of NFs that we have investigated here. So it looks, so 8, we have only 1 point. Okay, that's nothing, but 7 here looks like this is going to intersect the x-axis also quite before the continuum limit. Okay, if we now we tested this is a bit, because it's shocking, we tested this again on Wilson data, and this is quite neat. So this is the published plot on the left, which I have shown you before, with indeterminate extrapolations by ordinary polynomial. And the thing is, ordinary polynomial would be wrong for this situation. Okay, when you're intersecting the x-axis, you must have a tricritical point because you're changing from first to second order. And then you have to fit in the scaling variable, not in an ordinary polynomial. And all I've done here is I've taken the table, published data, rescale, and plot again. And this was, so this is double blind analysis, if you like. And you see now everything nicely collapses. You can do different order fits. The chi-squareds are better than the original ones, and get very little scatter in the intercept here, which would be a tricritical point. So the first order region is larger than in the staggered situation. And you can understand that because Wilson breaks chiral symmetry completely, staggered has a remnant of it, but in both cases it goes away, and the continuum limit is on the second order side in the 3 flavor situation. So we conclude that for 3 flavors we have prediction for a second order continuum phase transition, both for Wilson, order A improved or unimproved staggered. And then the Columbia plot, of course, looks different. Now this first order region in the chiral region is gone, and you have a second order line. And of course, our approach says nothing about what the universality class is. It only says it's second order. And that is a very exciting question, because it must be different in the 2 and the 3 flavor situations, because you have a different amount of chiral symmetry, I would expect. The critical temperatures have also been determined, and again, we're going to hear more about this from our colleagues in the next couple of talks. Okay, let's come back to the multi-flavor situation. So let me plot these extrapolated tricritical points here from the plot I've shown you before into a new plane, which we haven't looked at. So this is now the chiral limit, lattice chiral limit plane. Okay, AM is 0. And what I'm showing you is the tricritical line, NF versus N tau, or AT. And these are the extrapolated points. And I'm showing you a band here. We've assigned a generous error, trying different order fits here. And the tricritical line separates you the first order chiral transition from the second order chiral transition. Okay, and now you can ask where the continuum limit is here at 0, and where does this line end? Okay, my error band gets large, but not knowing anything else, it's going up. And now we're back to the talks from this morning. Our guess is that this will hit the axis in the conformal, in the point where the conformal window starts. And looking at these pictures, that's what inspired us. So this was looked at many years ago by FRG methods by Jens Braun and Holger Gies. They computed the chiral transition temperature as a function of NF, and it goes down, okay, and it ends at the conformal, or at the entry of the conformal window. And this was more or less verified by Maria Paula and Kotaro Miura on the lattice. So they have completely confirmed that you have a decreasing chiral temperature, but the order of the transition was not determined in these works. And what we are now saying is that you're certainly second order, let's say up until NF6, that's what we have explicitly checked. And then I would say what should happen in between. Presumably this goes all the way down to the conformal window. And by the way, this method of computing this tricritical line would be a method to get the NF star, or whatever you call it, your onset, quite precise, where you start the conformal window. Okay, so what about Pisarsky-Wilczek? This is in contradiction with Pisarsky-Wilczek, and I'm going to leave this for you to read later. But just to say, there is a brand new paper where this analysis was more or less repeated with somewhat different methods recently. So again, investigated was the RG flow of 3D sigma models, but now you go to the order phi to the 6. So you take a higher power, and it was done by not epsilon expansion, but FRG methods. And then you find additional fixed points, which are in principle consistent with the second order transition. So that seems to lift the apparent contradiction. Okay, and then here are my conclusions. So it looks very much like at zero density, chiral phase transitions are second order for all numbers of NF up to 6, certainly, and possibly up to the conformal window. And now it would be so that's true both for Wilson and Wilson has only NF3 so far. So it would be very interesting to check more flavors in the Wilson discretization as well. And of course, chiral fermions would now be something interesting to investigate. Thank you.
Thank you very much, Ove, for this very interesting talk. Questions?
No, it's not the same. So there is this. Yeah. So there is. No. That's physical QCD. So the crossover is here with physical quark masses. What I've been talking about is the chiral limit. The chiral limit, exactly. And then you cannot have a crossover. So then you are either first order or second order, and that was the question. And now, of course, the next question. So to what is the relevance for physical QCD? The next question is, this was also discussed yesterday already, how big is the scaling region here? Does the physical point feel anything from this universality class or not, and so on? So there are many questions. And it's also constraining the finite mu phase diagram, the chiral limit.
More questions?
Yeah, I apologize if you already mentioned it. You said that for Wilson fermions, the first order region is larger, and I don't fully understand what's the reason behind it, if you can comment.
Okay, so it's if what it looks like, this first order region is a cutoff effect, right? Because it goes away before you reach the continuum. And then the conclusion is that Wilson action, so any action has different cutoff effects. And the conclusion would be that the Wilson action has larger cutoff effects for this boundary than the staggered action. And my guess is that the reason is Wilson breaks chiral symmetry fully. So if you're investigating the chiral phase transition, you have to get much closer than if you have a lattice action with at least a remnant chiral symmetry like staggered. But it's a guess.
Okay, yeah, thank you.
In this Wilson plot, I know it's not, I think, yours, but the one on the left here, you said it's order A improved. Oh, sorry. So, well, they're both Wilson, but there's an order A cutoff effect in the.
Yeah.
I mean, why is that then? Is the observable not order improved, or?
The observable is not improved, so it's the action, which you would think should be enough when you're doing thermodynamics, because because you're looking for the partition function, but indeed you're measuring it with the chiral condensate. So that is one question. And also, I think they discussed in the paper, they have increased the in tau, and their beta range got larger than where the improvement holds. So it may be that they're, that the coefficient isn't needs retuning in this parameter range. It's beta dependent, right? The Clover term.
I have two questions. The first is whether the strong dependence on the lattice spacing means that the nature of the phase transition might depend on the UV physics if you start changing the physics at the cutoff. And the second question was if you know anything about larger NC.
Larger NC. So second question, no, I don't. That is of course expensive, right? You would have to repeat it again. So I'm not aware of more than 2 colors and 3 colors. And the first question, I would say, so if you look at the ratio of, so if you take, for example, the pion mass here, which signifies the boundary, and you compare that with the cutoff, right? The pion mass is the IR scale, which we are after, and then you look at 1/A, what is the value of the cutoff, then you see that we are just approaching about 1 order of magnitude, and I think that's the reason. The scales were not separated so very much. And another reason is, I think you put that forward in your 4-flavor paper, is if you think in terms of even in the continuum, finite temperature field theory, you have the Matsubara frequencies. And if you have on the lattice, your Matsubara frequencies run from minus n tau over 2 to plus n tau over 2. Okay, so you have only these small n tau's, you have only a few terms. I think that's the main reason.
Yeah, I mean, the temperature is quite close to the ultraviolet scale. So
exactly.
Maybe one last question, then.
Just a comment rather than a question about the second part of the question that was about larger NEC. There are some calculations by the grant. I don't think that they are conclusive, but I think that the question is still relevant. And the reason is that at a large NC, you do not expect quarks with finite mass to play a role in the dynamics. So which means that whatever you observe at finite mass, infinite mass of the quarks should carry down at finite mass of the quarks at n equal infinity, which means that at n equal infinity, for any finite mass, you will see a first order phase transition. So now it becomes a very relevant question, the interplay between the chiral and the large n limit, especially on the light of your results, Owe. I mean, there is a competing effect, and we know that these two limits do not commute. So yes, it becomes a very, very relevant question. Yeah, the end point of the Columbia plot will squeeze towards the axis. Yeah. So the dynamics of that will be very interesting to study.
Yeah, apologies. Actually, now I remember it. He did up to, I think, 4, 5, and 6 colors have been looked at. But yeah.
Okay, so I think it's time to thank O again.